Hello everyone. Today we're going to look at reduction of aldehydes and ketones. In the Solomon's 12th edition, there is no specific section discussing reduction of aldehyde and ketones. However, the information are included in multiple sections. So I'm taking them all out and summarize them over here. One of the most important chemical property associated to aldehydes and ketones are they undergo the nucleophilic addition reaction. Sodium borohydride as a hydride source could provide a nucleophile attacking on the carbonyl carbon, essentially after protonation generating the corresponding alcohol. And this reaction is irreversible. And along with sodium borohydride, lithium aluminum hydride and other hydride source could also act as the nucleophile to reduce aldehyde or ketone into the corresponding alcohol. In this case, because the reaction is nucleophilic, the carbon-carbon double bond will not be reduced. If we treat this same starting material with a catalytic hydrogenation condition with one equivalence of hydrogen, and the carbon-carbon double bond will be reduced and the carbon-oxygen double bond will not. So we can generate this aldehyde. So it depends on what kind of double bond you are inclined to reduce, you can control your reaction condition to achieve your synthetic goal. What if I want to reduce both the carbon-carbon double bond and the carbon-oxygen double bond? What you can do is you can treat this compound with rhyl-nickels under the catalytic hydrogenation condition. Rhyl-nickels is a finely divided hydrogen-bearing nickel. It is made by treating a nickel and aluminum alloy with strong sodium hydroxide solution. And under these circumstances, you will probably mechanistically first reduce the carbon-carbon double bond and eventually reducing the carbon-oxygen double bond, generating the reduction product. The other interesting reducing reaction of aldehydes and ketones are you could even further reduce aldehyde and ketone into the corresponding ch2 group. We call it a deoxygenation reaction. Okay, show you this example. This ketone could be reduced into the corresponding ch2. Okay, for this deoxygenation reaction, we've already seen this in the previous chapter, and I'd like to also help you to refresh some of that. Okay, and the first example we've seen is the Clemmensen reduction reaction. Let me move the page so you can see better. Do you still remember Clemmensen reduction reaction? Clemmensen reduction reaction utilizing zinc, amalgam, and the reaction typically carried out in concentrated hydrochloric acid solution with reflux. The reaction is undergo a very likely free radical reaction mechanism, converting a CO double bond into a CH bond. Okay, and this reaction on Solomon's 12th edition is discussed in section 15.9a in the electrophilic aromatic substitution chapter. Okay, and the next reaction is also discussed twice already in this semester. And this reaction is called the Wolff-Kishner reduction reaction. Wolff-Kishner reduction reaction utilizing hydrogen under basic condition, potassium hydroxide, not alcohol. And usually it also carries out in high temperature. So the reaction involves with reacting a CO double bond with hydrogen, essentially a primary amine, generating the corresponding imine, okay, a hydrazone. And this reaction is discussed in section 16.8 on the Solomon's 12th edition. Okay, and it is one of the very typical nucleophilic addition reaction as well. Once you generate hydrazone, the hydrazone could eventually turn into the corresponding ch2 group under basic condition, finishing up this deoxygenation reaction. Okay, and the Wolff-Kishner reduction reaction discussed in both section 16.8 and section 15.9b, along with the Clemmensen reduction reaction in the same chapter. And these two reactions are complementary. The Clemmensen reduction reaction is carried out under acidic condition, and the Wolff-Kishner reduction reaction is carried out under the basic condition. A reaction that's also related to what we discussed in this chapter also involved a reaction of an aldehyde or ketone with a dithiol, okay, and zinc chloride. Under that circumstances, your reaction undergoes a generation of the thioacetal. Okay, let me move the page up so you can see better. Okay, similar as generating acetal group, and now we're using generating a thioacetal. Okay, and refresh yourself about the mechanism about it. And this information is in section 16.7d on the Solomons. Okay, as I mentioned, the reduction reaction is all over the book. And so once you generate the thioacetal, this thioacetal could be treated with the renin-acose again. Okay, under a catalytic hydrogenation reaction condition, eventually you will dethiolate and generating the ch2 group. Okay, so maybe I should write renin-acose catalytic hydrogenation condition. These are the typical reduction reactions associated to aldehyde and ketone.